All right. Uric acid. Oh my God, why am I? Hey guys, in today's video we're going to go through a laboratory experiment where we're trying to experimentally determine the delta H of a reaction. So this would be the change in enthalpy of a reaction. We're going to do it using the neutralization reaction of hydrochloric acid and sodium hydroxide. Hydrochloric acid is a strong acid, sodium hydroxide is a strong base. When they combine together they form water, and sodium chloride, a salt. So what we're going to do is to experimentally determine this, we're going to use a calorimeter. Now we've already discussed how a calorimeter works, but we have a dual coffee cup calorimeter. It's a fairly rudimentary calorimeter, but a calorimeter that we can use to determine change in temperature. We're going to use, in order to mix our calorimeter, a magnetic stir plate and stirring rod. We're going to place the stirring rod into the actual calorimeter and onto the stir plate. Okay. Then what we need to do is take our hydrochloric acid and sodium hydroxide of two different concentrations. Now here I have 0.5 molar sodium hydroxide and 1 molar sodium hydroxide. I've got 1 molar hydrochloric acid and 0.5 molar hydrochloric acid. And what we're going to do is we're going to kind of mix and match these over the course of the lab. In order to be precise about this, I need to make sure I have two accurate measurements. The first accurate measurement I need is initial temperature. So all of these solutions will have been sitting out for a period of time so that they're ideally at the exact same temperature. What we're going to do is we're going to use a digital thermometer to measure the temperature of these solutions. Again, always make sure you're measuring in Celsius. And what we're going to do is we're going to go ahead and take 50 milliliters of my 0.5 molar hydrochloric acid, and I'm going to measure that out. Now, one thing to be careful of, I have two graduated cylinders here. I'm going to use one graduated cylinder only for hydrochloric acid and one graduated cylinder only for sodium hydroxide. I don't want them to mix at all until they're in the calorimeter. So I'm going to take my hydrochloric acid and I'm going to measure out 50 milliliters of it. Perfect. Now what I'm going to do is I'm going to place this initially into my calorimeter. All right, so I'm going to pour this into my calorimeter. Okay, again, that's my hydrochloric acid one. Now, with my sodium hydroxide, I'm going to do the same. I'm going to start in this case with 0.5 molar sodium hydroxide. I'm going to measure it out and then I'm going to wait. Perfect. So now what I have is I have 50 milliliters of 0.5 molar hydrochloric acid in my calorimeter. I have 50 milliliters of 0.5 molar sodium hydroxide in my graduated cylinder. Now, before I mix them, I need to do two things. The first thing I need to do is get my thermometer into the hydrochloric acid and measure its initial temperature. That's the first thing. So measuring the initial temperature of my hydrochloric acid. Then I'm going to start the stirring. You don't want to stir it too fast. Okay, but you need to get it stirring pretty good. If it's stirring too fast, you're going to see it start to splash. You don't want that to be the case. So we're going to stir our calorimeter. This is going to mix everything around. All right, and then what we're going to do is we're going to add the sodium hydroxide while continually measuring the temperature. Now the second I've added the sodium hydroxide, I'm going to pay very close attention to the temperature. I'm going to watch the temperature. The temperature is going to change. Now this process I'm going to tell you right now is an exothermic process. That means the reaction is losing potential energy. It's contributing kinetic energy into the solution. Thereby the temperature of the solution is going to go up. What we need to do is watch the temperature rise on our thermometer. Once it rises to a point where it stops rising and starts to fall again, that high point represents our thermal equilibrium. That's our final temperature. At that point, we're going to stop the process. We're going to go ahead and, because again, all that you have in this solution at this point is hydrochloric acid, sodium hydroxide combining to form water and sodium chloride. So all we have is water and sodium chloride. This can go straight down the sink. Be very careful with it because you don't want to accidentally dump your magnet down the sink as well. All right, so you can use a second magnet to prevent the first from going down the sink. So what we're going to do is once we find thermal equilibrium, we're going to stop, turn off, and then we're going to dump very carefully so as, again, not to make sure that we don't lose our magnet down the sink. At this point, we're going to rinse our calorimeter with water, and we're going to start the process over again with the next pair of our reactants. So let's head to the board and see how we can process the data we just collected. All right, now that we've collected the data, let's go ahead and look at how we're going to process it. We're going to start with a balanced reaction between sodium hydroxide and hydrochloric acid. Remember, we're starting in aqueous solutions of each. If we had started with solid sodium hydroxide, this actually would be a completely different problem because the dissolving process itself has an energetic component. So let's go ahead and start by writing the balanced reaction. Now in this case, we've got aqueous hydrochloric acid combining with sodium hydroxide in its aqueous form, forming water and sodium chloride. One thing to remember is this process, all right, has a net ionic equation of just H plus OH minus yields H2O, as does any strong acid, strong base neutralization. Now what we're looking for here is the heat of the reaction, delta H of the reaction. So how do we look for it? Well, remember what we collected. The data we collected involved So here's what we collected. Molarity of an acid, volume of the acid, molarity of the base, volume of the base, initial temperature, and final temperature. All of these are going to be utilized in our calculations. Remember, anytime we're looking at change in temperature, we're focused on changing kinetic energy. Where's that kinetic energy coming from? Well, in this case, the reaction. The reaction between hydrochloric and sodium hydroxide, as you saw in the demonstration in the video here earlier, that it's an exothermic process, right? The temperature of the solution went up to some extent. Now, the temperature of the solution went up, and we need to figure out by how much. So your objective in this lab is going to be to figure out how much the temperature of the solution went up, and then connect that back to our reaction to figure out what is the enthalpy of the reaction. So, how do we do this? Well, remember, anytime we're looking at change in kinetic energy, change in temperature, that means we should use an equation that involves changing temperature, mc delta T. Heat is equal to mass times specific heat capacity times change in temperature. So let's take a look at where these would go in here. So now that we've determined that we need to use this equation, let's figure out how and why. Well, here's the thing. Mass, specific heat capacity, and change in temperature are all connected to each other. They all have to be of the same thing. And in this case, it's going to be of the solution. So there are a couple of assumptions we're going to make. The first assumption we're going to make is that the solution, even though there's hydrochloric acid and sodium hydroxide in water, we're going to assume the density of the solution is equal to the density of water. And that's 1 gram per milliliter. The second thing we're going to make an assumption on is that the specific heat capacity of the solution is equal to that of water. Now, that means that the specific heat of the solution is 4.184 joules per gram degree Celsius. So we've got two of these variables because we know the volume of the acid and the volume of the base that we added. So if you combine the volume of the acid and the volume of the base, that gives us the volume of the solution. If we assume that the solution is 1 gram for every 1 milliliter, then we also have the grams of the solution. That's our mass. Specific heat we assume to be the C of water, 4.184 joules per gram degree Celsius, and change in temperature we calculated going final temperature minus initial temperature. Now, your job in this laboratory is going to be to collect this data, to plug into my MC delta T to figure out how much heat was released in each of our trials. Once you do this, then you can go back and actually calculate the delta H of the reaction. Because remember, going from heat to delta H, from Q to delta H, simply requires you to divide by moles. Moles of what though? Well, remember, it's moles of our limiting reactant. So you always have to remember that each of these reactions is going to be limited not just in terms of how much product's produced, but also by its energy using the limiting reactant. So the limiting reactant limits everything. So we're going to say, okay, if that's my Q that I've calculated, my delta H would be that Q value that I've calculated divided by the moles of our limiting reactant.